Okay, let's get started with Chapter 7 and decimals. Today we're going to talk about terminating decimals. Terminating decimals are a special kind of decimals, obviously, and I'll define them here in a few minutes. But let's start off by just talking about decimals in general. And money is always a great place to start, as money is a good place to start when you're talking about integers and introducing negative numbers. When you start talking about decimals, it's a great place to talk about it there as well, because most of your students are already familiar with money. So let's take $128.95. We can break that down into 128 plus 95 over 100 more dollars. If we break that 95 over 100 down even more, we can see that that is 9 dimes and 1 nickel. I know there's other ways to do it, but let's just keep it simple here. 9 dimes and 1 nickel, and a nickel is equal to 5 pennies. So we can break down 95 over 100 as 9 times a dime, which is 1/10 of a dollar, plus 5 times a penny, which is 1/100th of a dollar. Okay, so we'll talk about that more in a second, but over here I did add in this decimal place value chart, because I didn't want to write them all out. But you see what all the places here are, and we have this chart is very nice. The one thing that I would add to this chart would be the powers of 10. So let's add that. So 1 is 10 to the 0 power. 10 is 10 to the first power. 100 is 10 squared. 1,000 is 10 cubed. And 10,000 is 10 to the 4th. Also, the tenths, 1/10 is 10 to the -1, 1/100th is 10 to the -2, 1/1000th is 10 to the -3, and 1/10,000th is 10 to the -4. So continuing on with our example from the last slide with our $128.95, I've written it out in expanded form here. And then I've also extended it here to the powers of 10. Okay. It is very important for you to reinforce and use yourself the proper way to say numbers. And the proper way to write numbers. So I'm going to reinforce that in this particular PowerPoint here. So this is 128 and 95 hundredths. I know I have money here, but if we were going to write it as this, 128.95, that would be 128 and 95 hundredths. Notice a couple of details here. The excuse me, the dashes in the name, and also that we use the word "and" to designate the decimal point. Okay, so be careful not to inadvertently add in ands in your numbers. Don't say 128 and 95 hundredths. Okay, that would be a little gratuitous with that and does cause some confusion for students later down the line. Let's take a look at this one here. This is 52 and 3,467 ten-thousandths. I messed that up very bad. Let me look at it one more time. It's easy to mess up. You have to practice. Don't not practice. So this is 52 and 3,467 ten-thousandths. You could have also said 3,467 ten-thousandths. I don't know why I wrote it kind of awkwardly like that. But here we have it in the expanded form, and also we have it with the powers of 10. So let's write this one out in expanded form real quick. This is 6 times 10 plus, and this is a personal preference. I like to show every power down. So even if we're missing a digit here, I'm probably going to say 0 of them. Here we have 10 to the negative 1 plus 4 times 10 to the negative 2 plus 6 times 10 to the negative 3 plus 7 times 10 to the negative 4. And this is said 60 and when you go to say this last piece, you ignore the 60 and you look at the number behind the decimal point and say that number as if it was in front of the decimal point, and then you add the place value to the end, the hundredths, the hundred thousandths, and such. So let's look at this number. 60 and 23,145 hundred thousandths is how we say this. There's if you've noticed, the further along that we've gotten in what we've learned, there's less variety in the number of models and stuff. Makes sense because students have learned and understood enough to be able to apply the standard algorithm for things like addition, subtraction, multiplication, and division. So here we are using the concrete model with the base 10 blocks to demonstrate 3.4. Okay, now it's very important that you set what your values are going to be for your blocks. It's not the same anymore like when we use the base 10 blocks for whole number addition, where each the small block was a unit, the long block was for tens, the flat was for hundreds, the block was for thousands. Now you can set it for whatever you want it to be within reason, okay, because we only have so many different blocks. Okay, so here is 3.4, and I have stated what our legend is basically. I don't think I spelled that right at all. I put an extra D in that for sure, didn't I? Yeah. All right, legend. It just kind of lets us know what everything is out. And here we have 3 1 units and 4 single units. And this is 3 4/10. We can also interpret it in one group where you could put all of the blocks together. You could use individual blocks and make it out of individual blocks as well. But another thing that you want to continue to reinforce once you get to decimals is that their relationship back to fractions. So this is a way that we could also do it, and this also shows 34/10. So we're going to use some base 10 blocks and take a look at this number 2.235. Now notice that I have described what everything is going to equal. The block is going to equal 1. The flat is equal to the tenths place. The long is equal to the hundredths place, and the unit is equal to the thousandths place. Now I decided not to draw this out because I'm not the best at that, and I know it's a little tedious, so I did write it out, which is examples in all of our chapter 3 stuff on how we can write out the exchanges and do the work of the base 10 blocks without the actual blocks here. And so here I used, instead of the word and, we can use the word point, interchangeably. And so to say this, it is 2.235 thousandths. All right, decimals are modeled beautifully with the 100 unit grid. You're going to see tons and tons of 100 unit grid stuff coming at you here in chapter 7, at least for the next couple of sections. And as you see, I have modeled 0.7 and 0.56. And again, you would want to reinforce this to your students that this is, and you can reinforce it in a couple ways, this is 7 out of 10 rows, right? Or we also have the fact that it is 70 out of 100 units. The same thing here. But we don't have that even row, so the only thing we can really say here easily at this point is that this is 56 out of 100. Okay, let's look at converting fractions to decimals, kind of the technical way here. And I'm going to be using the expanded, oh, sorry, my foot's asleep, using the expanded algorithm. So first things first is I took our 25 over 10 and I rewrote 25 as 2 times 10 plus 5, putting it in that placeholder form, right? And then I split them into two pieces. Remember, when you have a operation on top of one denominator, that denominator actually belongs to each piece in that operation. So I split those 10s over, and then notice 10 divided by 10 actually canceled out, and that gave us this 2 right here, which I carried this 5/10 over, and 5/10 would be 0.5, and that is the way that we did it. Here I also did it with 56 over 100, breaking them apart. Now when you get to the 5 times 10 over 100, remember that 100 is 10 to the second power. This is 10 to the first power. So one thing we can do is we can employ our exponent rules, and it says when we have them divided, we can subtract them, and so that would leave us with 10 to the negative 1, which is 1 over 10. So that's one way we can look at it. But your students are more likely going to do this. Cross out the zeros. You get to match up the zeros there. All right, and then we go on here, and now we have 5 over 10 plus 6 over 100, and so we get 56 hundredths. Here finally, and I totally covered it up. I will write it out for us when we get to the end. I broke this 205 over this 10,000, broke it up the same way, except for this time I used those exponents. You can see how those exponents could be helpful to write it in that exponent form. So I wrote it in the powers of 10 here, and then here, of course, I said 2 minus 4 equals negative 2, so that's 10 to the 2 minus 4 gives us 10 to the negative 2, and there is our 10 to the negative 2 underneath. And then nothing changes here for the 5 over the 10,000. So the final reveal is 0.0205. Awesome. So we've been working with denominators that are from a very special group of rational numbers. Those denominators, every denominator we've dealt with has been a power of 10, which fits with placeholders, right? Because our Hindu-Arabic numerical system is based on powers of 10. So We can manipulate rational expressions so we can rewrite something into what's called a terminal fraction. And a terminal fraction is a fraction whose denominator is a power of 10. So let's look at these examples here. In this first example, we have 7 over 2 to the 6th power. And so we get to use the power of algebra and its trickery to turn this 2 to the 6th power into a 10 to the 6th power. And the way that we do this is we're going to instill this fancy 1, right? Because 5 over 5 is equal to 1. 5 to the 6 over 5 to the 6 is also equal to 1. So if we multiply the top and bottom by the exact same thing, we're not changing the problem, even though the look changes a little bit. We're really not changing the veracity of the problem because we're really only multiplying both digits by 1. And so we're going to bring in that 5 to the 6 because we already have a 2 to the 6, and 2 times 5 gives us a 10. So I put it together here, and we use those rules of exponents I've been going over, and we put it all together. I multiplied 7 times 5 to the 6, and I got this number, and then I was able to write it out, and that is our terminal decimal. And let's see, what is this number? Let's see, 10 to the 6th. It's not something I know right off my head, but 10 to the 4th is thousandth, so 10 to the 5th is 10,000, so 10 to the 6th is 100 thousandths. So this is 109,375 hundred thousandths. I don't want to write that down, but we said it. Okay, let's look at the next one here. Now this one is already given to us with 2's and with 5's, but they're not the same. Remember that that rule is that they have to be the same to be able to put them together. And so what we're missing is we need one more 2. Right? We have 3 and we need 4. So here I am multiplying by 2 to the power of 1 to be able to put this guy together. Now that we've put it together, that gives us 10 to the 4th. And so we can write this. This is 2, let's see, tens, hundreds, thousands, 10 thousands, 2 10 thousandths. That's how we say that. Okay, finally this last one here, first thing we need to do with this one is actually find that prime factorization. So I say, 250, and I like to go for the tree. That's usually my go-to when I do these things. So when we find the prime factorization, we see it's 2 times 5 to the 3rd power, so we need 2 more 2's. So we have equal number of 2's and 5's. Now that we've got that there, we multiply the top together and put the bottom and set it in its place. And this is 28 thousandths. Okay, now there's a couple of tricks here just for you, but you don't want to teach your students tricks. Okay, so if they're not sure what this is, then you're going to have to model it for them so they can see how that number is. how it goes and the way that it works with the zeros on the bottom. But you can see that there's most definitely a pattern you can work with. Okay, so we finally get to the definition and the theorem that deals with terminating decimals. A theorem, let A over B be an element of the rationals in simplest form, and that is super important, in simplest form. Then A over B can be written as a terminating decimal if and only if the prime factorization of the denominator contains no primes other than 2 and 5, because if we have a 2 or a 5, we can introduce the 2 or 5 that we need to make a 10. If there's no way to multiply to get a 10, then there is no way that it is a terminating decimal. So I ask you to determine here which one of these fractions are terminating. And you can tell by just looking at the prime factorization. So the first one, 7 over 8, 8 factors out as 2 to the third. That means that it is terminating, because we can just multiply it by 5 to the third over 5 to the third, and we're off to the races. This next one also has only 2's and 5's in it, so it is terminating. Next, we have 2's and 7's, not terminating because of the 7. I'm going to even say why. I almost always try to say why on things like that, especially if students are possibly taking any notes or whatever. And finally, this guy. Now, you have to be careful, and I want to point this out between the two of them. But this guy on first examination of the way 28 breaks down, you might say, well, it doesn't terminate. But check it out. If we prime factor the numerator 2, that has a 7 in it, and they actually cancel. So that being in the simplest form is very important. It has to be in the simplest form before you can declare it. So it indeed is terminating. So be careful. Okay. So the next thing we're going to talk about is ordering your terminating decimals, putting them in order. It's a big thing that starts in 4th grade. Decimals happen in 4th grade. Maybe a little introduction to them at the end of 3rd grade. But so placing them in order is really important, and you know it, right? But sometimes it's hard to see, especially for someone that is learning how to do this for the first time. So there are some ways to do it. One way is decimal grid comparison. Now, of course, when you do decimal grid comparison, that's using 2 different decimal grids. You've got to be sure that your denominators equal 100, right? Because the decimal grid comparison is 100 grid. Okay. You can also use the base 10 block comparison. After you determine what the legend is, you can look at them and physically look at them, but be sure to clearly define each place value. And then you can just do it using place value. Now, when you do place value comparison, and here we have an example of 6/10 and 6/100. Now, a lot of times students, when they hear you say it, they might think more quickly that it's the hundredths that's bigger, because when we go in the direction of whole numbers, 100 is bigger than 10. So you have to be very careful first to pronounce the hundredths and to make sure that they understand this. And the best way to understand that is to put them in the same denominator, okay? So you can compare apples to apples. So here we convert 6/10 to 6/10 and 6/100 to 6/100. And when we look at them, we can see that, and I don't know why I put an equal sign here. That was absolutely insane-o. Let's just put a big fat question mark there, because that's the question that we're asking. Which one is bigger? So I'm not really sure. Oh, now I see how I did it. Sorry, it's hard to see, but this is the comparison. So we converted 6/10 to 60/100, and now we're going to compare 60/100 to 6/100, so we can see that 6/10 is greater than 6/100. So let's do another place value comparison here. We're dealing with 345 thousandths and 1,489 10,000ths. Okay, so first we're going to convert to fraction so we can compare them. And then to get the denominators the same, I'm going to have to multiply that 345 by 10, so that gives us 3450, 1489. Once the denominators are the same, you can pull the fractions out of everything and just compare the denominators, and we see 3450 is greater than 1489. And so we can say 345 hundredths is greater, thousandths, sorry. 345 thousandths is greater than 1,489 10,000ths. Another way, and probably the most common way, or not most common, but a lot of people do it this way, is to do a decimal lineup. And so here are the two that we're going to compare. Let's see if I can say this without jacking this up. Tens, hundred thousandths, 10,000ths, 100,000. So this looks like it is 10,275 hundred-thousandths. And this one is 10, 100,000, 263 thousandths. Okay, so first I just wrote them as they typed in, and I want to point out that it's called the decimal lineup. So what you do is you line up the decimals, and then we put these trailing zeros. We add in the zeros. So they are the same size, so to speak. That actually does the same thing as converting it by multiplying it and doing that. So you can just kind of do it that way. Another way I like to think about it, and I kind of think it's cool, is especially if you've got a visual student, you want to build the array. You can build a rectangular array with those zeros. And of course, be sure to mention that this does not change the number at all as far as its value.